Hello, everybody. Welcome this morning. We have a lot of aspiring billionaires in the room, I see. I am Benny, and together with my friend and colleague Hans, we've been looking at blockchain technology for the past year or so, and we wanted to share with you everything we've learned so far. The talk is divided in two distinctive parts. The first one will focus on Bitcoin and how it operates, where does it get its value from, so we're going to dive immediately really deep. Then we're going to zoom out again and look at blockchain in general, because I'm already mentioning two different terms here, and what it can do in our day-to-day lives. And then we're going to look at Ethereum, which is another blockchain, and how you can develop applications with that. But first, Hans is going to tell you about Bitcoin.
So, has anybody heard about Bitcoin at least? Show your hands. Okay, most people. Someone already owns any Bitcoin, bought them? Okay, few people. Perhaps some miners who mine their own. Okay, very nice. So a lot of people have at least heard about Bitcoin, but at least in Belgium, when it's in the news, it's a lot of times in a negative sense. For example, this is the logo of the Silk Road, which was a website on the dark web.
Anybody use that?
Don't need to answer that. But what it is it was a marketplace where you can buy and sell drugs. But you don't use PayPal to buy your drugs. You use Bitcoin because it has some anonymity features, so it could hide your illegal activities. Another example is this thing. I think we saw it in a few slide decks over the conference already. It's the Wannacry virus, so a lot of computers got infected.
Anybody got infected?
That's nice. If you did get infected, the hackers were very friendly. They could decrypt your files again if you paid them some Bitcoin on an address they provided. And a lot of people actually did, so it's another thing, another example of Bitcoin coming in the negative news. But there are also some more positive use cases, for example, in the remittance industry. So a lot of people, a lot of times of poor countries, go to work abroad, and where they can earn more money than at home. And what they do is they send part of their earnings back home, but a lot of the time the people back home maybe don't have a bank account. So what they do is they use Western Union, so they go to the Western Union office, give them some of their money they earned that month. And what Western Union does is it makes sure that it transfers it over internationally around the world back to your family, and then your family can visit the Western Union office and withdraw the money. But actually this is quite expensive. The average is a rate of 8% on the amount you want to send. And it takes a lot of time as well, so a couple of days at least, sometimes weeks, depending on where you want to send it. But you could also use Bitcoin, so you could buy some Bitcoin with your money, send it to an address your family owns, and then your family can use the Bitcoin back at home or exchange it for their local currency. And this costs a lot less money, and it's a lot faster. So it's not all use cases of Bitcoin are negative ones. Quite some potential here. So let's take a look at how it actually works, because if you want to create a global money network, let's say, you need to solve a few things to be able to make this work digitally. So we're going to compare it with a ledger like this one. It's a book. So a blockchain is kind of like a ledger which holds all transactions that happen within the network. So let's say, for example, this old book is a ledger that holds all transactions of some medieval town. And yeah, when they need some money, they go collect some taxes from the citizens, and then they write down, okay, at this day I collected this amount of money from this person, and they write it down in their book. And when they collected a lot of taxes, perhaps they want to buy some horseshoes from the local blacksmith, so they write down the amount of money they paid to the blacksmith at what time, etc. So this book, this ledger, holds all transactions that happened with the money of the little town, and anyone can check the ledger and find out the complete truth in this book, and one person can write in it, and it holds all transactions. So we need a few things to make this work digitally, because the book is easy, there's one book, but when you want to distribute it over a global network, you need to solve some problems, so let's go over them. First off, you need to identify yourself, and the person you want to send money to, so you need something to keep track of addresses and be able to authorize yourself. And what is used in Bitcoin is public key cryptography, just like in HTTPS. So you don't go to some website, bitcoin.org, and register for an account. You just generate a random key, private key, and then a public key is derived from that, and now you have a public-private key pair, and you can take part in the Bitcoin network. So there's no central registry. You just generate your own key. You might think, well, if I generate my own key, isn't there a chance that I generate the same key as someone else, and when I have their private key, I can access their money? But the chance of that happening actually is quite low. The amount of possible combinations in a private key is 10 to the power of 48, which are a lot of zeros. And to give you an idea, the count of all atoms in the Earth is 10 to the power of 50. So that just means there's a lot of possible combinations. And in practice, that means that you generating the same key, the chance of that is zero. So you can't generate the same key. Important to note here is you generate your own key. Using that key, you can access your funds, so you need to keep your key safe, obviously. When you lose it, you can't go to the central Bitcoin office and ask for a new key. If it gets stolen, then it's simply not your money anymore. The other person now has your money. So you need to keep your private key safe. So what you don't do is something like this. There are these machines where you can pay with a regular old credit card, and you can buy some Bitcoins, and what you get is a piece of paper with a public-private key pair, which you can then use to add to your wallet. So you probably don't post on Twitter how happy you are with your first Bitcoin, because if you post your private key, then well, it's not your Bitcoin anymore. Simple like that.
So what's essentially, it's just like the regular wallet. If I leave this here on stage and move away, anybody can come in here and take my money. So it's essential that you keep whatever, in this case, just my paper wallet, that I keep it in my back pocket safely and secure. So we now have a way to play along in this global network. And how can we be sure that whenever we're making a transaction, that nobody is tampering with the data? With until a few years ago in Belgium, at least, you could use paper checks, which just a piece of paper. My name is printed on it. I can enter an amount. Somebody can I can enter the name or the bank account of somebody who I want to send some money to, and then this piece of paper, together with a pencil, I scribble on it, or like 2 dashes, and then that somehow meant the paper was secure. But which is great in the paper world, but as we move to the digital world, we need a better way to secure our transactions. And again, the public key cryptography can help us secure this transaction. So let's take a transaction which has an amount of Bitcoin I want to send and the address of Hans, in this case, I want to send Bitcoin to. How can we make this secure? Well, I take a hash of all of the data in the transaction, so the amount of Bitcoin and the address, for instance, and then encrypt that hash with my private key. I then get a signature. This signature is then added to the transaction and sent to the network. Anyone who wants to validate the transaction can then use my public key to decrypt the signature, and then they get a hash again. All of the other data is present in the transaction as well, so they can locally hash that as well. And when those two match, they can be sure that nobody has tampered with the data, and that I was indeed the originator of the transaction. So nobody has tampered with it, and it can be successfully transferred across the network.
Yeah, so now we can identify ourselves and create transactions and sign them. And now we can start sending them to the network. But the network also has to have a way to make sure that the amount of Bitcoin I want to send, that I actually have that amount of Bitcoin. And there's no such thing like a Bitcoin balance. It works a bit differently. So let's say I want to send a transaction to Benny. I want to send 10 Bitcoin. Then I create a transaction with output Benny's address, and the amount is 10 Bitcoin. And what I need to do is provide one or more transactions that happened in the past that amount up to the amount I want to send. So there's this list of unspent transactions that the whole network keeps track of, so that those are transactions that happened in the past and that haven't been used in another transaction as input. So in this example, I have transaction 1, where in the past I received 5 Bitcoin from someone else. And I have another one, transaction 2, where I received 6 Bitcoin. And I haven't spent those transactions yet, so I provide them as input for my new transaction. And for the people who can count, 5 plus 6 is 11, so it's 1 too much to be to make 10. So what you can do is also specify multiple output addresses. So you can, I'm going to provide Benny's address and send 10 Bitcoin to that one, and I'm going to provide one of my own addresses to send the 1 Bitcoin as change to, and then the amounts add up. And when this is sent to the network and validated, transaction 1 and 2 are then removed from the unspent transaction list. So I can't use transaction 1 anymore to send 5 Bitcoin to someone else, so I can't double spend my money, which is probably something you like in a payment system.
So we now have a way to validate somebody who takes part in the network. We have a way to validate transactions, and we have a way to make sure money isn't being sent twice. But who does the bookkeeping? Who is the one, if we take the analogy of the great medieval book, who has the feather who writes every line in the big book? And that's the job of the miners and the bookkeepers. So they receive transactions, and they are constantly validating them and trying to add another page in our big book. Since it's a distributed network, nobody really, they all have a part of the truth. And part is actually wrong. They have all of the truth. If you want to spin up a machine, you can just download a piece of software, and you can have your computer take part in the Bitcoin network. Well, the first thing it will have to do is download all of the history. Every transaction, every block since the inception of Bitcoin, which was from around 2008, will be stored on your machine, and then when that's finally completed, which is a few gigabytes it has to download, it will then be able to process transactions. Transactions are grouped together to form a block. Hence blockchain, we're getting there. But that's not all they do. Since all of those computers are constantly competing to find the next block of transactions, they need to solve a puzzle. They combine the hash of the previous group transactions combine that with the hash of the current transactions, and the Bitcoin network dictates that I have to solve the puzzle, which means when you combine those two hashes, it needs to be below a certain amount. So they need to find a random number so the puzzle can be solved. In the keynote, there was a mention of the trapdoor functions. Well, this is one of those. If you install it on your PC, you'll see that your CPU or your GPU will be at 100%. Your machine won't be able to do anything else. They're constantly trying to find that number that will solve this puzzle. And why do they do this? Well, they get rewarded when they find this, the solution. One computer will find a solution. Since it's very hard to find that random number, but it's very fast to validate it. So if one computer finds the solution, it will broadcast, hey, I found the next page in our book. This is the hash that I found, and this is the random number. And the other nodes will then validate that. So they can immediately see, oh yeah, node X found, let's say, number 5, and that does solve the hash. So we will be using his hash as the next, we will use his hash for the next block. So the entire process starts all over again. They will take the new hash as input, start mining the other transactions, and try to solve the puzzle again. They get 12 Bitcoin for doing this. 12 Bitcoin, I checked when we started the talk, it's a little more than 2,000 euros. So if you want Norwegian kroner, it's times 10. So it's very lucrative to mine Bitcoin. Does that mean, oh, great, I have some Azure credits I can spend. Let's just spin up some machines and install the software. Well, chances are very slim of you actually be able to mine Bitcoin. Although it's completely random, there's specialized hardware to do this. So, and since it's so hard, people are combining their computing power into groups. So if one node in that group finds the solution, they distribute the money between all of them. But if you want, you can take part of it. The miners get money from finding the blocks, which are, by the way, the only transactions which don't need inputs. Since, like we mentioned earlier, if I just want to send Bitcoin to Hans, I always have to specify other transactions. Only when the miners find the solution, they don't, of course, they don't have input transactions. They also get rewarded by processing transactions. There's a fee you have to pay in order to get the transaction processed, but the fee of that is negligible. In a certain point in time, there will the mining of blocks that will the reward for that will become zero. It's not like the central bank in Europe when they say, oh, the economy has some issues, let's just reprint, let's print some extra money. That's not something that's possible in Bitcoin. There's a set amount of Bitcoin. Currently, they are rewarded when they find a new block, but somewhere in the future, that will stop. That's built in the network. So that's the hash. So it's very compute intensive. At the moment, there are like 1 quintillion hashes per second in the Bitcoin network, and all of the computing power of the Bitcoin network combined is bigger than what Google has to offer. So it's very big. But why do all this hard work? Why do they have to find those hashes and combine them? Well, then we really are at the nature of a blockchain. So here you have blocks, which are linked together with arrows. What does combining all those hashes actually provide? So let's say we have block 3, which builds upon block 2. It uses the hash of B2 to create itself with the transactions which are part of the block. And block 2, same thing, block 1, etc. If I want to manipulate transaction 1, let's say I've sent 10 Bitcoin to Hans, but I want to be fraudulous and I want to change that amount to 5, or I just want to discard the entire transaction, that would mean that block number 2 would have to be recalculated. Because if anyone who has worked with hashes before, changing just a little bit of the data creates an entire new hash. And since the hash of block 1 is contained in block 2, you need to recalculate block 2 in its entirety. And since block 3 builds on block 2, you have to recalculate block 3 in its entirety again. And so on, and so on, and so on. And by the time I've recalculated all those blocks, the Bitcoin network is already much farther ahead. So I won't be able to compete to change all of those, all of the blocks together.
Right. So we've listed some key features or principles of a blockchain. Period. So we have this single distributed ledger, and Bitcoin obviously has that one too. So you have a single ledger, as in there's one version of the truth. It's just all transactions that happened in history. But it's distributed, so everyone has a copy, and everyone can check if everything in it is correct. It's immutable due to the the chain of blocks and the hashing. So that makes it effectively impossible to mutate. In theory, it's possible if you have a lot of computing power, but that probably costs more money than just not changing the history. It's trustless, so you don't need to trust the person you send money to or get money from. You don't need to trust a single computer in the network. You just trust the system as a whole, and the hashes, etc. The hashes are actually the cool thing about this, if you think about it. And it's automated, so you can build stuff on top of that. You can make some cool applications that automatically send money, etc.
So that's enough talking for now. Let's take a look at the Bitcoin network in action. Oh, it's too bad that all the things are in the way. Here you see a live view of all transactions across the globe. So you see them popping up. You see here a list of transactions. So whenever somebody who makes a transaction, it will appear here on the map. So we have some in Sweden. Come on, somebody send some Bitcoin, and we'll see Norway pop up. Here you can see, if I zoom perhaps, that somebody is sending Bitcoin in Lithuania, in Germany, and I can here click on the link, and then you see the transaction. So somebody is sending 390, or even more, $2,500 almost. There's one transaction as input, and two transactions as output, which is again like the story we mentioned earlier. This person had one transaction with a lot of Bitcoin behind it and wanted to send it to somewhere else. He probably wanted to send this amount, 2,055, to somewhere else, and his change is being sent to another address he owns. We also see here that's an unconfirmed transaction. What does that mean? Well, this, the work of finding the hashes and finding a next block, it takes some time. If I send for this amount of dollars to somebody else, I want to make sure that the transaction has been processed, I need to wait for like 20 minutes, because you need to the entire process of finding a block and the next one and the next one, and make sure that the transaction that's sent to me has been validated enough time, and that I'm part of the network. You need to wait 20 minutes to be sure that the money you received is really in your account. This ticker also has here the amount, by the way. So I opened this when we started the talk, which was 23 minutes ago, and it's like almost 9,000 Bitcoin have been transferred, times 2,000 euros. You have a large number. Anyone? It's a lot of money. So those are the transactions over here. Here I can see the blocks that have been mined. So during the talk, 25 blocks have been mined. So 25 new blocks with transactions have been added.
It's 8:30, actually.
Yeah, but it's not local time. I think it's UTC or something. Here we see that the block has a name. I mentioned earlier that a bunch of people are working together in a group. They combine their computing power. Well, one of those is the BTCC pool. And if a block has been found, and we know exactly where the IP, etc., lives, we can give it a name. Again, I can click on it, and I can see here the hash that was found, the hash of the previous block. They got $30,800 for finding the block, and I can see all of the transactions that are part in this block. So again, we mentioned earlier, using Bitcoin gives some anonymity, but I can just see whatever's happening in the network. Yeah, I can't say whoever owns this, I can't find his name, and that's the anonymity. But let's say if I want to exchange this for something else, and for that, let's take a look at which one was this? It's this one. The Wannacry authors, they specified the Bitcoin address where you had to send money to. Well, they had like 6 different Bitcoin addresses, but this is one of them. So what did they receive? In this address, $48,000, almost $49,000. So these are all people who have sent Bitcoin to the virus authors. Sometimes it's most of the time like $300, $400, but sometimes there are very small amounts. I guess it's sympathizer or whatever. If I was one of the authors, what do I have to do? Well, if there was a marketplace which I can use Bitcoin, then I might be able to buy something with it. But if I want to create dollars or euros or whatever from it, I have to send this money to an exchange. And there are a bunch of exchanges out there, and they allow you to transfer or convert Bitcoin into other cryptocurrencies or in dollars or euros or whatever. And then there's a central place. So if law enforcement tries hard enough and the authors aren't so smart, then they can be found. So actually, this money is currently a bit locked in here. You can do a lot of complicated stuff, like sending the money around to several addresses and splitting it and combining it. So you can make it very hard. But you need to. It's not that anonymous as you think, because I could show you all of the transactions in the network and what's located everywhere. There's one point which you might have seen on this map, which is like over here, which is 0 longitude, 0 latitude. That's just transactions which have been sent where we can't really know where they happened. So they get located over there. Any questions about Bitcoin? Yes. Yeah, we can hardly see anything with the light, so.
So is there a limit of transactions that you can store? And like another question, you said that you need to download all the history of the transaction. So what happens if it grows exponentially, like not several gigabytes, but terabytes?
Yeah. So the man here asked, is there a limit to the amount of transactions and how big does it grow? Well, one block, by the way, is currently about 1 megabyte. And there's an entire debate about scaling Bitcoin. By the way, if you currently, I don't want to lie, how big is the entire history? It's gigabytes now, it's not that
more
big.
More than 100, but not 200.
And that's all of the transactions since 2008. So that's still okay-ish, but since it's open source, you can't. There are Bitcoin improvement proposals, and there's currently an active debate on how can we change it. How should we have bigger blocks? Should we store information? Should we store less information in the block? Maybe there's something that should be left behind next to it. Do we really need all of the information of the previous blocks? So that's an ongoing debate, actually. Yes?
What is the size of the hash, and what is the current boundary, and how quickly it moves up?
So you ask, what's the current hash and the binary, and how big, big
do you mean the hash, the puzzle they need to find? Or? Yes. Yeah. There's actually a mechanism that makes it harder if more computing power is added to the network. So it makes sure that the average time that you can guess a block is like 10 minutes. So if a lot of computing power is trying a lot of different hashes, then the block is found faster than 10 minutes, but then they increase the difficulty, and then it's back 10 minutes. So it's a lot.
We want to answer all of your questions, but since we're time limited, just come to us after the talk, and then we'll try to answer all of them. because we want to look at something else as well. The sample which we mentioned earlier, the Western Union example, that's like textbook example. You want to have an example on where can I use Bitcoin or blockchain technology? Yeah, it's always fintech which is mentioned. But for this talk, we wanted to give you a broader vision. Just let's not focus on all the financial on the financial world. Certainly there are benefits, but can't we think of another way that we can use this technology? And back in December, Hans and I were sitting down and we were talking about a process in Belgium, and that's how we can buy a house. I don't know if it's like this in the rest of the world, but this is how it works in Belgium. Well, first you decide I want to buy a house, so you go on the housing market, search around, and then you finally find something which kind of fits the bill. So there's always work and etc. So things you have to do, but this is the house I want to buy. So I meet the owner, he guides me around, and theoretically, if I had enough money to pay him upfront, law forbids me from doing that. There are some legal steps I need to take. So we need to introduce some notaries in the system. At least one, but most of the time it will be two of them. One of them does actually do something. The other one is there just to make sure the other guy isn't fooling around. What's the first thing he does? Well, he collects my identity card. Every Belgian has an identity card. And although there's a chip on it, most notaries just ask for the card and then write your name, first name, my address, my place of birth, my birth date, and my registry number. Every Belgian has a unique number. He writes that down, and he will contact the federal government. Could you please give me the details of Benny? And could you please give me the details of Hans? And then they compare the two. Is indeed the one who wants to buy this house Benny, and is indeed the one who is selling this house Hans? So when those match up, he will then contact the Flemish government, the local government. We have a lot of governments in Belgium, to get more information about the house. When was it built? When was it rebuilt? Are there any building violations? Isn't the house part of an existing loan, etc., etc.? All of that information is gathered to draft a document, a piece of paper. Then there are also these guys, the bank. Most of the time, or at least when I wanted to buy a house, I didn't have all of the money in my wallet. So I go to the bank. They also repeat this process. Are you really Benny who is coming here? Even if I am a customer with them for a very long time. And they don't just give me the money. No, they give it to the notary. It's strange. I've been a customer for years. Why you don't give the money to me so I can buy this house? So they give it to the notary. And when all of that's completed, and the day is finally there to sign the official document, we read the document, and what do we see? That's not how you spell my name. An error on this page, an error on that page, etc. So we correct it, and then finally we get to buy the house. How long does this process take? Any ideas? A month? I hear 6 months. Well, by average, it's 3 months. Now, let's say if I sell this house again, I have all of the documents. It'll go faster, right? No. They repeat all of it again and again. So, can't we use a blockchain in this example? And what would it improve? Well, instead of having the housing information, for instance, spread across multiple agencies, let's put that in a blockchain. So we know when was a house built, when was it rebuilt. Let's store that information together. What does that provide us? Well, I can, at the moment, contact my government to get like the basic properties of the land size, like how when was it built. That's information I can query. But then I get a piece of paper. Anyone with a scanner and a printer can create a piece of paper. So if we would store it in the blockchain, we would be certain that the information is correct. We would introduce a lot of trust in the system. Currently, you have to introduce the notaries, which have to get paid. The government, apart from the taxes, which I always have to pay every year, takes 10% of the total amount just to make the transaction. The bank, apart from the loan I have to pay every month, I also want a fee because I want a loan. Introducing the blockchain to automate this entire process would eliminate a lot of needs, for the intermediary, the notary, and I wouldn't have to spell my name again when we sign the document. So it's just an example of how the blockchain could be used in another way. But we can't build that with Bitcoin. Bitcoin offers some programming capabilities. Let's say we want to build an eBay, and eBay takes a fee for every transaction, and if, even if everything goes fine. But if you can model that construct with a middleman who just gives you the money when the other one agrees, something like that can be modeled on Bitcoin. Does that mean that if you may leave this talk, I'm now going to build an eBay on the blockchain, somebody was first. So that exists. Bitcoin is really centered about sending money to somewhere else. It's a cryptocurrency. But how can we create something as complicated as buying a house on a blockchain? Something like that exists, and that's the Ethereum blockchain. Ethereum is essentially, you write a piece of code, you compile it, and you then send it to the blockchain. And instead of just sending money to left and right, we call functions on the blockchain, on the application which we deployed, and we have to pay a fee every time we call a function. A piece of software deployed on the Ethereum network is called a smart contract. There are two networks, a production Ethereum network, which you can use for production, and a test network. So if you want to fool around, you can create a contract and deploy that on the test network. But you can also just deploy your own Ethereum network. In the sample we'll show you in a bit, Azure actually offers that. You can, in a few clicks, create your own private Ethereum network to create applications on.
So when we wanted to play around with this, so we thought of an example that we could model in a smart contract. We came up with a game like rock, paper, scissors, lizard, Spock, because 5 options are better than 3. So what we made is in general. So there are 2 users. They just want to play rock, paper, scissors, lizard, Spock. But one of them, like Benny, is in Australia, and you can't meet in person. So, but you want to make sure that no one is cheating. You don't trust Benny. You don't trust a central game server. You don't trust anyone. So we want to use a smart contract. So I'll send my hand, Benny sent his hand, and then the smart contract will determine the winner. And everything is transparent because you can just check the code in the smart contract, see if cheating is indeed impossible. And that's what we made. So let's take a look. Spoilers. Yes. So I can visit this website, which hosts the game, and then I'll choose the first one, which is another tab. I'm going to play against myself. And let's say I'll choose rock. Okay, I'll send my hand, and then where's the other tab?
Somewhere.
Do your Mac magic. Here.
There it is.
Right. Oh, I got a. This is in Australia. So I got a challenge from me, and I want to win, so I'll play paper. Right. And now what happens is we need to wait because things are happening in the blockchain and, well, transactions and stuff. So we'll come back to this later. And let's take a look at how this works. So this is a broad architectural image. We have a web server which just hosts the UI you just saw. It has a SQL database which contains non-critical data like a friendly name. Don't need that in a smart contract. And then we have a blockchain network. We deployed our own in Azure because It's easy. You just click a few buttons. Azure spins up some virtual machines, creates an Ethereum network, and gives us like all the Ether we need to test out smart contracts.
Ether is, by the way, the currency of Ethereum. Just like we have Bitcoin in the Bitcoin network, if you want to pay for something in an Ethereum network, you need to pay Ether.
Right. So that's cheaper. And then the web server can access the network to ask about stuff, and the client can as well. So let's take a look at the flow we implemented, because when we built this, we wanted to limit the amount of calls to the smart contract, because, like we saw, whenever you call a smart contract and you want to change the state, for example, you want to store a hand, it takes time and it takes money. So especially the time is annoying, because you want to know immediately if you won or not. So we came up with something more complicated. Let's say I want to play rock, and I say, okay, I select rock, and I generate a random salt on my client. I hash those two together, and then I send that hash to the web server, and you can store it. And then we wait until player 2 selects his hand, let's say paper, generates his own random salt on his client and hashes that and sends that hash. And now the web server has both hashes. It doesn't know which hands were played. And it can create a contract on the network, on the blockchain network, using those two hashes, and that starts the smart contract. And that's the operation we were waiting for. So it needs to create a transaction, wait for it to be mined, etc., before you can actually call stuff on it. And when that happens, an event is relayed, and then the clients can reveal their hand. So they just send the hand they selected, the random generated salt, they stored and send it to the smart contract. Then the smart contract can check, okay, if I hash the hand and the salt together, is it the same hash that was used to create the smart contract? If so, then I really played rock, so I can't change my mind. And then the other player does the same thing gets checked, and when the smart contract received both hands, it can calculate the winner. So rock loses against paper, and so then the winner is
found,
determined. And so important to notice is that you didn't need to trust anyone. You didn't need to trust the web server for it couldn't change your hand because it didn't know your hand. It just had a hash. You didn't need to trust the other player. It couldn't know your hand before you. If you sent your hand, he couldn't make out what it was because it was hashed, etc. So you didn't need to trust anyone.
So, what does that actually look like? Let's first go to the smart contract, because that's probably something you didn't see before. This is a smart contract. I have Visual Studio Code open, which has an extension for Solidity. If you want to create an application for Ethereum, you need to learn the Solidity programming language. There's also an extension for Visual Studio, but it doesn't have color coding, so I preferred this one. The first line here specifies the compiler I'm using. So that's to prevent when the contract is deployed, I don't want to have a different behavior when there are new features available. So that's what I specify over there. And then there's the name, the contract, blind game. You can see most programming constructs which you're familiar with. I can have a glorified integer over here, the state, rock, paper, and so on. I can declare events that the contract will be outputting. I can create struct types which, for my data structure which I'm using. And then here you can see public members of the contract. Nothing special over here, but then we come to the constructor. Function bind game, and we see here address player 1, player 2, and then bytes 32. And the two hashes which the server has, which were sent to the server, are then transmitted to this contract. I assign them to the different variables, I add them to this array, and I also have this special contract. The message isn't defined over here. There's no parameter message, but that's just who is calling this function. Because everybody has to pay when calling functions. That's all metadata which is combined when you call a function. So I can get the address of the person who is calling this. In this case, this will always be the server address. If I want to send Ether when I can inspect that as well. Then there is something like this, which is another function, but here I specify it's constant. It just reads from the blockchain. Reading is for free. You can read as many times as you want from the blockchain. Writing data, changing the state, that's where you need to pay your fee for. The fee which you use in Ethereum is called gas. Then there's this little helper function I wrote. There's no concept of null or whatever in Ethereum, which is great. You won't have null reference exceptions, but it's not so great if you want to check if something has been initialized. So you need to write some helper functions to do that. Then the rest of it is just plain code. There's nothing really complicated here. So it's like the reveal hand. When the two hashes have been sent to the Ethereum network and the contract has been mined, then the clients will call a reveal hand. They will send their unencrypted, unhashed, whatever hand they played, like rock or scissors, and the hash they used. And then make sure that if player 1 is sending this, then we need to check whatever player 1 played before. The blind hand contains the hash. We hash whatever comes in, and if that matches, then we can be sure that player 1 is really sending rock or paper or whatever. We do the same for player number 2, and when that all completes, we can find a winner. So declare winner. Let's scroll there. Let's say if there was a draw, and keeping track of whatever was played, and then calling the event is just calling the name draw with all of the attributes I wanted to call. So it's not that complicated. Certainly it can get more complicated. There are many more programming constructs in the language, but just to get this little demo going, you don't need to learn a lot. So we compile this, and I'm using Truffle, which is a framework that can help me, and that it outputs this JSON file. This JSON file contains two important things: the ABI, or Application Binary Interface, which is like the whistle of WCF or the Swagger from a REST service. It describes what functions are present on the contract and how can I call them, with parameters, do I have to pay when I call them, etc., which is very long. And then there's the unlinked binary. If you want to call contracts on the blockchain, you just need the ABI. If you want to deploy contracts, you also need the binary. What does Truffle provide us as well? Well, I can write tests for it. Here we see with Mocha, I can simulate an entire game on the blockchain. I'm connecting to a test blockchain on my local computer, and then write a test just like you would for your other web development thingies. Nothing special over there. So we have the contract now written. Let's interact with it. Well, let's take a look at our server. Here you have the play hand functions. So this one is called with the salted version for the two players. And when we have collected both of the hands, we then can call, I have queued this here, we can then create the address. I'm using another framework for that, in Ethereum, which you can find on GitHub. So I'm deploying the contract over here with the ABI and the binary, and then pass in all of the constructor arguments. So just C# a way of interacting with the smart contracts. You need to wait for it to get mined, etc. And then I update some more information. I can get a reference to the events, so I can start polling for the events whenever they occur, etc. And then let's say there's the API, the web application. We wrote a web application in Angular. If you want to interact with it from JavaScript, that's also possible. You can do it natively with the web provider of the Ethereum network, but I'm using Truffle again. So I import Truffle, I give it the ABI in the binaries, and I can then call methods on it as if it was just a JavaScript object. Here I'm saying, give me a reference to the contract that was deployed at a certain location, and then call this method on it. So it is possible to interact, to create applications that run on a blockchain and interact with it from JavaScript or from .NET.
Did we win already?
Yes, you lost, or you won, depending on which game.
Or both. All right. So this code is on GitHub. We'll share the link later, so you can check it out. Yes, some lessons learned using Ethereum and all technology around it. So we did actually succeed in our mission to play rock, paper, scissors, lizard, Spock without any trust between us and any server, so that worked. But it came at a price. What you saw, the speed, whenever you do something on the blockchain, because of everybody is mining and checking, it just takes longer. So that's something to keep in mind. And yeah, the cost as well. We rolled our own Ethereum network, but when you want to use the actual Ethereum network, there are a lot of more users there. So demand, supply, the Ether just costs more. So it's costs more money. A centralized system is obviously more efficient. It's also cutting edge, which means it's code speak for not so easy to work with. If there is documentation, then a lot of the time it is deprecated when you read it. We tried the example, the Hello World example some time ago, and it wouldn't even compile.
So you just copy paste it from their website into the Visual Studio Code or their own development environment, and you press run or compile, and it already crashes and blows up.
And sometimes you need to call this undocumented API to be able to do what you want to do. So yeah, it needs some work, but it has a lot of potential. When you do want to do things without trust, it works. So there's that. Well, you might think, oh, cool, I want to build a blockchain app, but just make sure that the use case you're thinking of really needs a blockchain, because as I mentioned, there are more, a centralized system is more efficient. But yeah, there's a lot of hype right now, and a lot of companies, especially in fintech, are now jumping on it. But yeah, there are not a lot of really useful use cases, if you think about it. For example, you have this thing, it's called Dogecoin. It started out as a joke. It's actually just, it does the same thing as Bitcoin, so you can send money. And everybody was really hyped and bought a lot of Dogecoin, and then the developer stole all the money. So, oh, project is dead. No, if you check it out, you can find a list of all cryptocurrencies, and when you look it up, it's actually number 20 of most market cap coins. It has like $300 million worth, but it's nothing. So.
Then again, the example we mentioned earlier of buying a house, we thought of that around December, November last year. And then you see here 2 articles from May and April, where Sweden and the UK are actively developing something like that. You can, and even on the UK, on that article, there's a link for job applications. So they are trying to experiment with this and put that information in the blockchain. Because you might say, certainly, I trust the government to store my data, but that's today perhaps, and tomorrow there's somebody else who says, oh, all that land information we have, that doesn't exist. That archive we had, they'll just burn you down. So we can use blockchain for certain official documents, etc. Like in the Antwerp, where I live, is now looking at storing my driver license, etc. in the blockchain. And all of the all of the documents that they have to give, like if you want to work for a, what's it called? if you're going to work for the government, I need to provide that. I need to provide a document which says I'm a very nice person. I didn't go to jail, etc. Well, anyone with a printer can create the document, but if they can contact the blockchain to get that information, then they can be certain that nobody has a fraudulent document. Another example of a blockchain out there is the Everledger. One of its use cases is diamonds. Normally, every diamond gets engraved for it to be identified, but again, in Antwerp, the machine was developed to remove that. So you can't be certain where the diamond came from. So what does the Everledger do? Well, they combine a lot of characteristics of the diamond and the documents and put that on the blockchain. So whenever diamonds are traded, they can look at the Everledger and verify, hasn't this diamond been stolen, or where does it come from? Does it come from a conflict area, and so we shouldn't trade it, etc. So that's a gap, bridging the gap between the digital and the physical world. There are more proof of concepts out there. Like we mentioned earlier, a lot of financial industries are looking at it. They are not so hyped about a public blockchain, but there are a lot of banks who actually want to create their own private blockchain, so they can reduce costs, and our transactions would be handled by that blockchain, because banks don't trust each other either, and they need to create other organizations on top of that to validate the transactions, etc. All of that cost could be deleted by using blockchain technology. So that was our talk. We hope you learned something, and we'll be here to answer some more questions. We'll put the slides and etc. Out there on Twitter, so you can read up the code and find reference material. And I hope you enjoy your day. Thanks for listening.